Good afternoon. I welcome the viewers to this problem solving and live interaction session for the subject Strength of Materials offered by Professor K. Ramesh on the SWAYAM portal. So, today we will be discussing the contents of week 7, which has to do with torsion. So, before we begin, I'll introduce myself. My name is Ganesh Ramaswamy. I'm a doctoral scholar in the Department of Applied Mechanics and Biomedical Engineering, working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department. So, let us move on to the first question of the day. It asks, the shear stresses induced in a solid circular shaft due to a twisting moment varies from where to where and how is what is asked. So let us look at this. Granted, we are we are holding this session 1 week prior to when torsion is being discussed. So anyway, when the viewers would see the lectures, the torsion formula will be derived threadbare there. So I will avoid digressing into that derivation. Rather, I will show the application part so that it becomes easier for the viewers to take up the assignment problems. So when we have a shaft, when we say a circular shaft, so it's something like that. So if this is subjected to a twisting moment, if this is the axis of the shaft, let us say, so the twisting moment could be shown like that. And naturally, the twisting moment at either ends would have to be opposite in nature so that the material gets stressed. If these are of the same nature, then it would just lead to a rigid body rotation about the axis of the shaft. I hope the viewers can appreciate that. This is one way of representing the torsion. Another way of representing this torsion is by a double-headed arrow like that. And how this is to be interpreted is we point our thumb in this direction and see how our right hand thumb in this direction and see how our fingers curl up. So that will give the nature of the torque applied. So these two are identical. All right. So for a shaft that is subjected to such a twisting moment, I'll call the twisting moment by some MT. So this is also MT since this is in equilibrium. So if I were to take this shaft, bring it here, and let me cut a section. Let me cut a section here and remove the rest of the shaft. So mind you, this is the cut portion of the shaft. So in the cut portion, in fact, I would rather make it dotted so that it becomes clear. So this is the cut portion of the shaft, which is dotted. So here, along the axis, we have shear stress varying like that, which will go from 0 to the maximum value. Actually, it will be, yeah, it will be something like this. So this is tau max. And if we are dealing with an r theta coordinate system, so this would naturally be r. Our direction perpendicular to that will be theta. R cross theta will be z in a cylindrical polar coordinate system. So I have r like that, let us say. I have theta like that. I bring it here. So this will give me z pointing in this direction. This is r and this is theta axis. And it is to be kept in mind that this would actually rotate from point to point. I'm taking the point here. If I take the point here, this will be r, this will be theta. If I take the point there, this will be r and that will be theta. So it will always have that right hand this thing nature, because r cross theta is z. This is r. In case that is not clear, this is r. All right. So under the action of this torsion, now first thing is to, our first idea is to relate tau. This is tau max. At some generic point, this will be some tau, which varies from 0 at the center to the maximum value at the outer edge. So we want to relate tau, and if we were to put the subscripts here, which one will be put? We can see that this is along the theta direction and in the z phase, positive z phase. So this is actually tau z theta. So our idea is to be able to relate tau z theta to the externally applied torque and mt. So we want to relate these two, and these are related as follows, which is one part of the torsion formula. So let us say that this has a diameter d, so therefore radius of the shaft, not to be confused with this r, this is radius of the shaft. Let me call that rs just for convenience and clarity. So r is d by 2. So from the torsion formula, we have tau z theta is nothing but mt by ip into rs, I should say, where mt is the actual torsional moment, twisting moment applied. ip is the polar moment of inertia. That is, ip will be izz here because z is pointing out of the plane of the cross section. So ip will be izz. Rs is nothing but the radius of the shaft. In fact, I shouldn't say rs, I should say just r. When r is equal to rs, tau is equal to tau max. So this is the actual relation. So this is one part of the torsional formula. Let me select this, no fill. Here also I should put no fill. Yeah, all right. And the second part is, so now we have been able to relate the stress to the applied stimulus, that is mt. Like we were doing in our axial case, in our axial member, we were applying a force P, and at some point we were able to relate the stress to P by simply P by A. Another thing we related there was delta. What is the change in length? So delta was PL by AE. So we first relate stress and then the deformation. These two are the quantities we want to relate for every type of loading. Initially, we have already seen it for axial members. Now we are seeing it for torsional members, which twist. shafts basically. So we have been able to relate torque to the twisting moment. The same image, if I were to take and I remove this. So let us say under the action of this line, that is scribed on the outer wall of the shaft. Let me remove this also for clarity. So this line, under the action of this twist, let us say it gets deformed like that. So therefore, this angle, this is denoted by phi, and the angle that it subtends on the center of the cross section, this is denoted by theta. And granted this is, let us say, this is of length L, then the shear strain is given by R. It will be this distance by the length. And what is this distance? It is nothing but R theta. If this is R in a circle, if this is the radius and this is theta, then the length of the arc is nothing but R theta. So the shear strain is nothing but R theta by, in fact, let me mark R theta with some other color. Yeah, let me mark it with green. So this quantity is R theta. So this is nothing but R theta by L. So this is the shear strain. So we know that this is shear stress and this is shear strain. So now we just further from our constitutive relations or the Hooke's law. So let us also put, so this is gamma z theta is R theta by L. So therefore, using Hooke's law, we get tau z theta is equal to G into R theta by L. So substituting what we get, on substituting we get mt by R into IP is equal to this quantity, R theta by L. So therefore, the twist that the cross section is undergoing can be written as mt L by, I'm sorry, I forgot the G here. The G would come here. So this will be mt by G IP. So this is another result we have got. This is one of the results we have got. So similar to an axial member where we were able to relate sigma axial is equal to P by A and delta axial, that is change in the length, is equal to PL by AE. Similarly, for a torsion for a shaft, we have been able to relate tau is equal to M by IP into R, and we have been able to relate theta is equal to ML by GIP, MTL by GIP. So these are the two fundamental quantities that we want to find out for anything. Why? Because this should not exceed a particular value or the material will fail because of the peak stress. As we saw in the tension test, it breaks off at a point. So this, if it goes beyond a limit, we know that shear can be resolved into tension and compression in a different coordinate system. So if the tension exceeds the strength, then it will fracture. Similarly, we don't want excessive twisting of the member also. We don't want it to twist too much. So we have calculated these two. Now let us look at the question back in hand. It says the shear stress induced in a solid circular shaft due to twisting moment varies from maximum at the center, minimum at circumference, minimum but not zero at the center, maximum at the circumference, zero at the center, and maximum at the circumference. So we know this is the correct answer with with the background of this discussion. So let us look at this. Which one is the preferred design approach in the case of a long circular shaft subjected to pure torsion? So what they have said is I have a shaft like that. It's pretty long. So whether it is strength, stiffness, both, or strength based on hollow and stiffness based on solid. So what this question is trying to ask is that if I were to apply this with MT, I see that this is L, this L, and the L is quite given to be quite high because it's a long circular shaft is what we are told. So what will happen to theta? Theta we are saying is directly proportional to L. So a line like this will have a large shear strain. There will be a huge shear strain and a lot of twist, in which case it might lose its functionality. But on the other hand, if we see look at the stress, we are able to see that stress is only a function of the cross-sectional parameters, namely IP and R. It has nothing to do with the length. So this will not govern, rather the twist will govern, in which case we call it that the stiffness criteria would govern the shaft design generally. In order to measure the shear strength on a circular shaft subjected to pure torsion, shear stress on a circular shaft, a strain gauge can be pasted in any other direction or perpendicular to the axis, pasted parallel to the axis, pasted at 45 degrees. So let me just take the same shaft and bring it here. Let this be subjected to a, an axial uh, twisting moment like that. So at any given section, if I remove this, so at any given section, I know this would be applying the same nature of twisting moment, in which case if I take an element here and I draw the element like that, I can see that the shear stress would be this way. It's a case of pure shear. It will be this way. But we also know the Mohr circle for this case is it is like this. The Mohr circle for this case is like this. So if this is our x, then we know when we rotate by 45 degrees or by 270 degrees or by minus 45 degrees, however you want to call it, we would actually have tension and compression. What this implies is if I take this and if I rotate it by 45 degrees like that, because in the Mohr circle it is 90 degrees, in the physical plane it will be 45 degrees. So if I rotate like that, at this point, on this plane, there will be no shear stress, but there will be a tension, or rather the tension would be this way, and compression. If this is tau, this will also be tau. And we know that a strain gauge can measure only axial strains. So we should ensure that our strain gauges are pasted at 45 degrees with the axis so as to measure the tension or compression. From from the strain that is measured, we can directly calculate the stress, and that stress happens to be the same value as our tau, shear stress. So let us look at this question. For a shaft shown in the given figure, identify the correct twisting moment diagram. So let me draw the shaft. The shaft is like that, and then I have a twisting moment of 100 Newton meter. At this point, I have a twisting moment of 60 Newton meter, and this end is fixed. So let me take this and get to a new page. So here it is similar to what we did for beams. So we have been given a sign convention and we have been given the coordinate system. So this is our coordinate system, which is positive z, and we have been given this as the sign convention. What this implies is on the positive phase, this type of twisting moment is positive. On the negative z phase, this direction of twisting moment is positive. That is what is meant by positive mz. So far so good. So now let me label these points. Let me call this A, call this A, call this B, call this C. Now, similar to what we used to do for beams, I'll make a copy. I will cut a section like that. And let me erase the rest. And let me join it by a dotted line like that. So this is the cut section. Now this I know is the negative z phase. On the negative z phase, this direction is my positive mt. So let me indicate positive mt is this mt. Now this under sigma m about z equaling 0, sigma m about z equaling 0 gives us plus 100. Why plus 100? Because this is pointing in the positive z direction. So this is plus 100 minus mt at some z. So let this be like this. So wherever we have cut, it is at some z, some value of z. So mt at z equaling 0. So therefore mtz equals 100 Newton meter. And where is this valid? It is valid between this point and that point. So what is z here? Z is 500 mm. From z equal to 500 to z equal to 1500, this is valid. So therefore, for 500 greater than z greater than 1500. So this much we have got. Of course. So far so good. Now I do the same exercise, but instead this time I cut the section in this place. So what do I get when I cut that section? I'll get everything except this, which is again at some z. This is at some z. Now again this is a negative z phase, so I have to point mt in this direction, and this is considered as positive mt. Now it is just a matter of applying equilibrium equation again, equaling 0. So this is plus 100 Newton meter, and this is minus 60 Newton meter. Why minus 60? Because this is pointing in the opposite direction to our z coordinate. We are adding mz, so this is minus 60, and this will be minus mt equaling 0. In fact, let me follow the color code for better clarity. These two are red. So therefore, mt comes out to be 40 Newton meter. And this is valid for 0 equaling greater than z, 0 less than z less than point B is at 500. So from 0 to 500, mt is coming out to be this. From 500 to 1500, mt is coming out to be this. So it is just a matter of plotting this. It is just a matter of plotting this. So we can see that option A, and this is the positive direction. This is negative. How do we make that out? You can see where the axis is intersecting. If it is below that, it is negative. If it is above that, it is positive. So we can see that this is the correct answer for this. Very well. So we'll move on to the next question. So this is how we draw the twisting moment diagram. Identify the correct statements. Shafts of square cross sections cannot transmit torque. This is categorically incorrect. Shafts of square cross sections are used in multiple tools. In fact, if you look at the Allen key, it is a hexagon cross section, but it has to transmit a twisting moment, a torque. So this is incorrect. A tension spring resists a tensile load by developing a torsional moment. So a tension spring, if I were to draw one, just for the sake of our discussion, I'm drawing it like that. So this will be a smooth transition. So if we see, if I were to cut this at any section, we will see that it actually transmits the load by twisting. So this is correct. Making a circular hole in a shaft will reduce the torsional stiffness drastically in proportion to the amount of material removed. So we know the torsional stiffness is GIP. As the viewers will see in the coming week, this is what is the torsional stiffness. So when we remove, when given a material, if we were to take a circle and then remove some material out of it, we see that IP is nothing but integral r square dA. So the farther away the material, higher will be our IP from the center with respect to the centroid polar axis. In this case, this is not true. It doesn't drastically reduce like this. Open sections have poor torsional rigidity. Yes, this is shown in the lecture also. If we take a hollow circular shaft and then just put a very thin slit along its length, it totally loses there is a drastic drop in its torsional capacity. So this is true. So let us look at this question. It says determine the torque in Newton meter which a shaft of 30 mm diameter. So there is a shaft. I don't want to keep drawing the shaft, so I'll just draw the cross section. And this is 30 mm. It can transmit without failure if the maximum allowable shear stress, so tau max, is limited to 60 MPa. So now we know this. So here what is given is tau max is given. So 60 MPa should be equal to some mt that is applied by the polar moment of inertia. The polar moment of inertia of a circle is using perpendicular axis theorem. IP is nothing but Ixx plus Iyy, and we know that Ixx for a circle is pi d power 4 by 64 plus the same thing because of symmetry. So therefore this comes out to be pi d power 4 by 32. So this is pi d power 4 by 32 into r. R is nothing but my d by 2. So therefore what do I get? 60 is 16 mt by pi d cube. If I don't replace this with 60 and rather say just tau max, this is a very celebrated expression for shaft design. Excuse me 1 minute. Just a moment. Okay, so this is given to be 60 equals some mt by 16 mt by pi. D is 30 cube, or mt comes out to be 30 cube pi into 60 by 16. So this is, we have been asked in Newton meter. So this E minus 3 will be in Newton meter, which comes out to 318.09 Newton meter. So what this implies is, if we were to apply a torque to this shaft of magnitude that is less than this, of a twisting moment magnitude that is less than this, then it will not exceed its maximum stress. That will be safe away from the stress point of view. So consider a solid shaft and a hollow shaft. Anand, think he left room. Consider a solid shaft and a hollow shaft of the same material and cross-sectional area. The outside diameter of the solid shaft is 200. So I have a solid shaft and a hollow shaft. Let this be the hollow shaft, like that. So this is hollow and this is solid. All right. So this has a, consider a solid shaft and a hollow shaft of the same material. So this is of the same material, same color, so same material we can take. And cross-sectional area. So area solid and area hollow are same. So this is given in the question. Further, it is given that the outside diameter of the solid shaft is 200 mm. So this is given to be 200 mm. And the inside diameter of the hollow shaft is 170 mm. So this inside diameter is 170 mm. Outside diameter we have not been given. Determine the outside, which is the first question, by the way. That is why this constraint is given. So therefore, we know that this is 200 squared pi by 4 is equal to d outer. Let me call this d outer. So d outer squared pi by 4 minus d inner is 170. So from here, solving for d outer, it comes out to be 4 by 5 square root of this, comes out to be 262.49 mm. So this much we know about the hollow shaft also now. So this is 252. All right. Determine the ratio of the maximum torque that can be transmitted by the hollow shaft to that of the solid shaft, is what is asked. So what is the maximum torque that can be transmitted by a shaft? So we know that for a shaft, for a circular shaft, tau max is mt by ip into R max. So therefore, for a solid circular shaft, IP is pi d power 4 by 32. R max is d by 2. So therefore, tau max for solid is nothing but mt by, substituting this, we will get 16 mp by pi d cube. So this is for a solid shaft. Now coming to a hollow shaft. Similar to area, we have to subtract out the moment of polar moment of inertia also of the inner this thing, because there is no material inside, which gives us for a hollow shaft IP is pi d outer power, pi d outer power 4 by 32 minus pi d inner power 4 by 32, and R max is d outer by 2. So therefore, tau max is nothing but, this will come out to be 16 mt by pi 16 mp by d naught by d naught power 4 minus d inner power 4, d outer power 4 minus d inner power 4. So if I were to take this common, this will become 16 mp by, if I take d naught common from the denominator, it will be pi d naught 4 power 4 common from the denominator, it will be pi d power 4 into 1 minus d inner by d outer, this power 4. So if I redefine this as some r, if say ratio Rd is given by di by d outer, d inner by d outer, then tau max for a hollow section is given by 16 mp by pi d outer power 4 into 1 minus Rd power 4. This will not be 4, this will be cube. Okay, so now the ratio, what is asked in the question, it is asked what is the maximum torque that can be transmitted, that is mt hollow, mt max hollow by mt max solid is what is asked. I hope you can read it. So this is what is asked. So now let us evaluate. In fact, I'll just put this as a subscript. This is hollow. This is solid. So we just a matter of taking the ratio. So let me go here and let me go here. So it is just a ratio of these two, but we have been told that it is of the same material. So if it is of the same material, then our maximum, because our maximum this thing is what is asked. So when will this be maximum? When shear stress reaches its shear strength. So these two are actually the same. So therefore, ratio of these two gives me 1 into 16 mv solid by pi d cube into pi d outer cubed into 1 minus rd power 4 by 16 mt hollow. So therefore, the question asks what is mt hollow by mt. So I take this by this quantity is equal to what? 16 gets cancelled. I'll just copy this and remove whatever is not there. To this quantity where the 16 and pi gets cancelled. 16 and pi gets cancelled. So yeah, this we have taken to the other side. This won't be there. This also won't be there. So this comes to d naught cube. So I'll just rewrite this a bit neatly. This comes to d outer cubed excuse me, one minute. D outer cubed into 1 minus rd power 4 divided by d cubed. So this is the expression for that ratio they have asked. So let us quickly plug in the values. So we know that this quantity is nothing but d outer was coming out to be 262.49 by d of the shaft is given to be 200, I suppose. 200. 200 this cubed into this cubed into 1 minus RD. RD is D inner by D outer. That is 170 by 262.49 the whole cubed. So therefore, this quantity is equal to 170 by 262. No, it's not cubed. I'm sorry. This is power 4. I hope you can see it. Power 4. 1 minus this into 262.49 cubed by 200 cubed. So this comes to 1.86. So what does this tell us? This question tells us that when we have two shafts, one hollow and one solid, of the same cross-sectional area, the hollow one actually has a greater moment carrying capacity, twisting moment carrying capacity. I hope that is clear and the viewers are able to appreciate that. All right. All right. So let us look at this question. It says a stepped shaft is subjected to torque of magnitude 50 Newton at the free end, 50 Newton meter at the free end of the shaft, and another torque of magnitude 250 Newton that is applied at the step. So this is a stepped shaft. So whatever torsion formula we have derived, it is only valid for a solid prismatic shaft that is of the same cross section. So it is valid for this, it is valid for this separately. It is not valid together. So what we can do, we can superimpose the response of these two over one another and get our answers. All right. So positive z-axis is marked. Consider the modulus of rigidity G is given to be 80 GPa. Very well. Answer the following question according to the sign convention is what is said. So let us see. Now we know that this is our positive z-axis. So if we were to keep our fingers, keep our thumb, right hand thumb pointing in this direction, we can see that this direction coincides with the curl of our fingers, which means this is positive 50. Similarly, this is positive 250, positive torques. So I can simply replace this with a normal diagram like this. Just the side view I'm drawing. It's like this. And of course, this is monolithic, so it's like this. So I have a torque of 50 Newton meter applied. And here there is a torque of 250 Newton meter applied. This length is given to be 450 mm. This length is given to be 800 mm. So this is point C, B, and A. One can see from the diagram, this is point CBA. So this is fixed. And the diameters. This is of diameter 50 mm. This is of diameter 25 mm. So we have simply drawn the question, we have redrawn it in terms of a simple diagram for us to be able to handle it easily. Determine the twisting moment diagram experienced by AB. So now I will not draw a cut section as we did in the previous case. We will do it quickly so that we get a practice of doing this quickly. So I don't have to do any big this thing calculation. So I need it for this section. So I put a cut here. I delete the rest. I know this is positive 50, and on the left face I will have that pointing in the opposite direction. MT will be pointing this way. This is positive MP. Both are equal to each other because one is negative of the other and sum of both is equal to 0. So therefore this is equal to plus 50 Newton meter. So applying the same logic, we can see y. Okay, determine the twisting moment experienced by the segment BC is asked. So using the same logic, we can see why this would be BC would have been 50, but another 250 is applied in the same direction. So therefore, this will be 300 Newton meter. So far, so good. We have been able to get this comfortably. All right. Determine the angle of twist at point B. So we have derived the expression for angle of twist. Let me just refer back to that. Where have we? Yeah. So this is our angle of twist. Let me copy and go back there. Yeah. So this is my angle of twist. So it is to be noted that this angle of twist is between two points. We select one as the reference and we see the other and see how much it has moved. So therefore, now if I take theta, for theta B, I take it to be theta CB. Between C and B, the section if I consider, theta at C is 0, it is fixed. Theta at B, it will have some twist. So that is what is to be found, will be equal to MT in section CB into L of CB by G of CB IP of CB. But we know it is a homogeneous shaft. It's the same material. So it doesn't, I can just simply put G here. Rest everything is changing because it is a stepped shaft. So therefore, we need to compute these quantities. So let us go ahead and do that. So we just found out what is this MT, what is the twisting moment that it is experiencing. It is 300 Newton meter. So Newton mm for consistency, I'm just writing. Into length. Length is, what is the length of this segment? It is 450 by G is given to be 80 GPa, so E3 into IP. The diameter of this section is given to be 50. So IP for a circular cross section, it is solid. So it will be pi d power 4 by 32. So therefore theta CB is also equal to theta B, because theta C is 0, is nothing but 50 power 4 into pi by 32 into 80 E3 into 300 E3 into 450. So this comes out to be 2.75 E minus 3 radians. But the question asks it in degrees. So this we must not forget. We have to convert this. So therefore theta B in degrees is this quantity into 180 by pi. This is the conversion factor. So this comes out to be into 180 by pi, which comes to 0.158 degrees. So therefore theta B is 0.158 degrees. What this means is when the torque is applied on the shaft, point B with respect to point C, point B rotates by this much. It is not even 15% of a degree. It is almost It is exactly 15%, 16% of a degree. So it's very less. That is what I meant to say. All right. So far, so good. Now the next question is determine the angle of twist at A. Now A is interesting because this is my angle of twist between 2 points. This is the angle of twist between 2 points. So for twist at A, theta BA is nothing but what we are doing here is we are holding B constant as fixed and then rotating A with respect to B. But B itself has a rotation. We will add that later. So another way to write this is what we want twist at A, we want it with respect to the free end, with respect to the fixed end. It is a total twist, which is given by theta C with respect to B plus theta B A with respect to B. So let me just clear out the nomenclature here, otherwise it will be confusing. Theta B with respect to C is, this is fixed and this is with respect to fixed. So in this case, we first hold B firmly there and then let A twist with respect to that. Then keeping this twist, now we hold C firmly because it is anyway held firmly, it is fixed. Now we let B rotate with respect to twist with respect to C. So the total twist of A will be the sum total of these two. So this we already know. We just calculated this 0.158. This we need to calculate. So let us go ahead and calculate. I'll just take this again. Let me take this also. So therefore, theta C with respect to A is 0.158 degrees plus this is MT BA L BA by G IP BA into 180 by pi because we want it in degrees. So it is just a matter of substitution. So let us go ahead and do that. MTA is nothing but 50 Newton meter. LBA is, what is LBA? It is 800 mm into 800 mm by G is 80 GPa and IPB is, what is its diameter? It was 50 and this is 25. So this will be into 25 pi 25 power 4 by 32. So let us calculate theta CA, what it comes out to be. It will be this quantity plus what does that quantity come out to be? 25 power 4 into pi by 25 power 25 power 4 into pi by 32 into 80 E3 E3 into 80 into 180 by pi. E3 to 800 now divided by 80 E3 divided by 25 power 4 into pi by 32 to 180 by pi. So 0.747 degrees. So therefore, theta Ca is nothing but 0.905 degrees. So this is what it comes out to be. This is the twist at A, maximum twist at A with respect to the fixed end. So here we are able to see that this quantity is much higher than this. Why? Because that portion is much smaller in its diameter, so it will twist more. Whereas this is a bit higher, this bit on the higher side. All right, so this is done. So this comes out to be this much. Determine the maximum shear stress experienced by the shaft. So what will be the maximum shear stress experienced by the shaft? This is just a nomenclature, I'll put that here. So the maximum shear stress experienced by the shaft can either be in portion AB or tau BC. So tau AB is 16 MTAB by pi DAB cubed, which is nothing but 16 into MTAB is 50 into 50 E3 by pi DAB was 50 cubed. I hope that is correct. No, this is 25, which comes out to be 16 T by pi D cubed. It's coming to 16.3 MPa, and tau BC is same thing with subscripts BC. So I'll just replace those. This is BC, this is BC, which is 16 into what is the torque it is experiencing? It is 450 by pi D is 50 cubed. So this comes out to be 16 T by pi D cubed. So this is 18.33. 18.33 MPa. Oh, okay. So this is not 450. 450 is the length of that. Actually, it is subjected to a torque of 300. Sorry about that. So this is 300 Newton meter. I hope it is clear to the viewers. 300 E3 by pi into D cubed, which comes out to be 12.22 MPa. So which is higher out of this? It is clear that this slender portion is experiencing a higher stress. In fact, let me move these around. Let me not make it cluttered like this. So this is there. Take this over there. So the question asks it is this or that. Therefore, tau max is experienced by portion AB. So this is portion AB, which is of the magnitude 16.3 MPa. So this is the maximum shear stress experienced by the shaft anywhere. All right. Okay. Well, I've run out of questions, so I would rather stop here. I would encourage the viewers to who are interested to take a look at the lectures first for this week, which will be dealing with torsion, and then revisit this live session if you are interested. Perhaps you'll be able to appreciate how to apply what we have learned in the lecture in problems, and hope you'll be able to do the assignment problems easily. All right. Thank you. We'll stop here.